Right, so this is the first of the 6 markers. I'm just going to turn the pointer on. And this one is a stationary waves question. You've got sound waves coming from the loudspeaker here, travelling along, hitting this closed fixed end of the tube, reflecting, and then moving back that way, back from right to left. And all the time, fresh sound is coming from the loudspeaker, and those two sound waves are interfering, and the displacements are adding together. Now, as with all stationary waves, what's special about them is that at some places the waves will be interfering constructively, so they'll be adding together to give a maximum, and that's called an antinode. And there'll be other places where the sound waves are cancelling each other out, the displacements add together to give you zero, and that's a node. And that is what we're seeing over here on the oscilloscope. So the microphone is turning the sound into a voltage, an alternating voltage, and the oscilloscope is just a voltmeter showing how that voltage is changing. So where the sound is loudest, you'll have these peaks and troughs, and where the sound is kind of quiet or zero, you'll have these places here. So these bits here, where the displacement is nothing, are our nodes, and these places here are our antinodes. And there's a scale here as well, so every horizontal square represents 0.5 milliseconds, so 0.5 times 10 to the minus 3 seconds. So you've got a complete wave, an up and a down, and that takes 1, 2, 3 squares, 3 divisions, so it's 3 lots of 0.5 milliseconds, 1.5 milliseconds. So the answer to the question is explain why you get maximum and minimum intensities of sound within the tube, and then work out the speed of sound. So this is my answer here, and if you look along or have a look at this and have the mark scheme, which is on the end of the question sheet on Google Classroom, so have that in front of you as well, and you can see where the marks are coming here. So the first couple of points, we're saying that sound is travelling along the tube and reflecting, and that's the first line in the explanation section of the mark scheme. So sound reflected at closed end, we've got that, so the sound is reflecting from the closed end. Then you are explaining or stating that there's interference between the reflected wave and the wave that's coming from the loudspeaker. And that becomes quite a tricky thing to put into words. So this phrase here, this incident wave, instant sound wave, is a really quite useful sort of term for the wave coming directly from the speaker. So the reflected and the incident wave interfere, and that causes stationary waves to be created. Then we've got the antinodes being the maximum intensity, and the nodes being the minimum intensity here. And that's our 4 kind of marking points for the explanation section. And then the next part is working out the speed of the sound. And if you look back at the graph, at the oscilloscope screen, you can see that there's a gap between the antinodes. Actually, ignore that. I'm talking rubbish there. In the question itself, in the information you're given on the question, it tells you that the distance between the antinodes, the distance between one maximum and the next, is 0.26 meters. It's in the information before the oscilloscope trace is printed. So we need to remember that the gap between the antinodes is going to be half a wavelength. So if you move between one antinode and the next, you're moving along half a wavelength. And try sketching out the stationary wave pattern just to prove that to yourself. Therefore, the wavelength is going to be 2 lots of that 0.26, which is 0.52 meters. When we're working out the speed, what we're trying to do, we're going to be using the equation v equals f times lambda. So we need to know lambda, the wavelength, and we need to know the frequency. So we can measure the time period, that's from the oscilloscope screen. So we said that before, that one complete wave is 3 divisions, 3 squares. Each square is 0.5 milliseconds, so the whole wave takes 1.5 milliseconds to do one complete oscillation, so it's 1.5 times 10 to the minus 3 seconds. Frequency is 1 over that, and then speed or velocity of the wave is that frequency times by wavelength. This bit here, we need to remember that frequency is 1 over the time period, and similarly time period is 1 over the frequency. So we put these numbers in, so frequency times wavelength, and we get a speed of 346.666666666 and so on milliseconds. Everything here is given to you though in two significant figures, or two significant figures, so our answer should be the same, so 350 milliseconds. If you pause the video now and have a go at the second 6-mark question, which is the measuring Planck's constant experiment, and then when you've done your answer for that, we'll have a look at the mark scheme for that question. Right, so these are the answers. So you've got 2 graphs, one which has kinetic energy against frequency for group A. So that's all, these groups are different people doing the same experiment on excuse me, from how I read it, the same material, and they're measuring the maximum kinetic energy of the electrons which are emitted from the material through the photoelectric effect, and seeing how that depends on the frequency. And each one of those groups recorded a different value for the Planck's constant, with a different uncertainty. And we're being asked to work out, or to explain first of all, how you can use that graph to get a value for H, and then have some kind of discussion about accuracy and precision. So we're looking for what accuracy is, what precision is, and what this kind of method might be. So anything which has Planck's constant and kinetic energy in, we are thinking about this equation. This is Einstein's equation. So the energy of the incoming photon, HF, remember H is Planck's constant, F is the frequency, is equal to phi, the work function, that's the minimum amount of energy required to cause an electron to be released, plus the maximum kinetic energy. And this equation is just a conservation of energy thing. So this is HF is the energy in, and that energy is going towards freeing the electron and then giving it any excess energy with which to move off. So from that equation, and using y equals mx plus c, if we plot kinetic energy on the y-axis and F on the x-axis, we could rearrange that into the form y equals mx plus c, and it would be Ke equals HF minus phi. And that means minus phi, that's minus the work function, will be the y-intercept, which we don't really care about in this question, in this experiment. And H will be the gradient, because that's the thing which is coming before F, which is our x-axis value. So what you would need to do to get a value for H is to use those kinetic energy against frequency graphs, draw a line of best fit, a straight line of best fit, draw a nice big triangle, and measure the gradient by doing rise over run. Then you need to think about accuracy and precision, and this is really trying to get as many different points about those down as you can. So you've got absolute uncertainties, so 6.3 plus or minus 0.3 and 6.6 plus or minus 0.6, because both of those are, so I'm saying both of those because both for group A the 6.3 and the 0.3, and for group B the 6.6 and the 0.6, they are all multiplied by 10 to the minus 34. We can ignore that 10 to the minus 34 and work out what the percentage uncertainties are. So for A, it will be 0.3 divided by 6.3 times by 100, and for B it will be 0.6 divided by 6.6 times by 100. So we can work that out straight away. And if you get a question like this, sometimes it is just the case of sort of saying everything you know about that particular area that is still relevant and not taking lots and lots of time to do. Another observation we can make looking at those two graphs is that for Group A, their results form a much better line. There's less spread around the line of best fit. And this ORA here stands for or reasonable argument. So saying that in other words would be okay. So B, the value of H, we could say is a little bit more accurate because it's closer to the real value. But it's not that precise because the percentage uncertainty is larger, certainly larger than the percentage uncertainty of A. Whereas A, it's more precise because of the smaller percentage uncertainty, but it's less accurate because it's not as close to the true value of Planck's constant. So go back through that, make any corrections, and make sure that's all in your online exercise book.